Hello and welcome back to ElixirZone. It has been 7.5 months. I am not dead, fortunately. I am taking advantage of the beautiful fall day to try to record this outside. I hope the sound works out. I will be praying for that. I apologize I know a lot of people have been interested in this channel and I'm super excited about that. I apologize, my job has kept me very busy. I took today off to finally record this episode. I actually took last Tuesday off as well, planning to record it, but I ended up spending the whole day tweaking and improving the presentation. There's so much material, there's so much I didn't know. I've spent a lot of time staring at metaprogramming and trying to understand it because it's complicated. I'm excited to share what I have learned. It's actually so long that I could not get this live view to work without crashing. So I had to split it up into two separate live views, and I will record and present the first live view in this recording, and then we'll do a separate recording for the second half of the material I've prepared, which will the second episode will go into much more of it'll summarize various talks that other people have given on metaprogramming. There are many great talks, so I'll sort of survey some of the main interesting things I've learned from other people's presentations. I'm trying to present something. There's so many great presentations out there. Most of them are half an hour, 45 minutes, maybe an hour, and there's so much more to metaprogramming that no matter how great any of those videos is, it's only going to cover a fraction of metaprogramming, and I certainly do not have the capability of presenting all of metaprogramming because, as I will discuss shortly, I'm not an expert, but I think I know quite a bit about metaprogramming at this point, enough to help beginners and intermediates level up. Not an expert, but we'll get to that. So also, I 7.5 months ago was working very hard to prepare some talks on biology and lessons that I feel biology has to teach scaling software and hardware systems. I have continued to delve deeply into biology over the last 7.5 months, read many books, watched many videos. It's totally fascinating. I think there should be a field for combining biology and software. It's sort of a systems engineering mindset. Biology are very complex systems that have evolved over time, and software systems are very hard to scale and keep running smoothly. I think there's a ton of lessons there. I've been slowly learning them. I will not be presenting them today. I don't know when I will. Eventually I will. But if you want to sort of get a glimpse of some of the stuff I've been looking into, I've provided some links here. Michael Levin is a professor at Tufts who's done some amazing stuff. I've watched a ton of his videos. They're mind-blowing. I highly encourage you to watch Michael Levin's stuff. I've put one example talk here. There are many more. Nick Lane is another professor of sort of biochemistry in England, I believe. And he studied mitochondria and the origins of life. Here's one talk, for example, how does chemistry come alive? I've really enjoyed learning from him. I've bought all his books. I haven't listened to them all yet, but he talks a lot about mitochondria, which sounds like a very obscure topic, but is actually pretty critical and fascinating. Robert Signer has he's I think at UCSD, has some real interesting talks on aging, and this one particular talk is sort of, he speaks for the first half, and this other woman from Israel, I believe, speaks the second half. Both talks are really engaging and fascinating. There's a professor at Cornell, Steve Strogatz, who's a mathematician, but he has some really fascinating research into synchronization. I don't know what just happened. Oh, I didn't want to click on that. Synchronization. And I really enjoyed this talk by a woman in Ireland at Dublin University on memories. But that's just a scattering of things I've watched. There's so much. It's so fascinating. And then these are a whole bunch of books, most of which I've read at this point. There's many more that I have purchased but not gotten around to yet. But if you are interested in learning more about biology and possibly how it relates to, or could be applied to software, these are very interesting books, and I will someday be talking about them, or at least some of them. But let's move on to metaprogramming now. So first I want to give some words of encouragement. Metaprogramming, let me sort of take this off the screen so we can focus on the words of encouragement first. So metaprogramming is Chris McCord. I'm going to reference his book quite a lot in this talk. He has a book that he wrote years ago called Metaprogramming Elixir. It's thin, it's dense, it's extremely good. It's confusing the first time you read it. I need to stare at a lot of stuff, see it from different angles, but I've reread the book now and it's making more sense. But he said on page 104, metaprogramming is basically abusing Elixir syntax for fun and profit, which sounds interesting. It is very powerful technique. I keep clicking, I don't want to do that. But it's hard and confusing and frustrating to learn, at least it has been for me. We're used to writing code. Metaprogramming requires a sort of brain shift relative to ordinary coding. We're going to go through lots and lots of examples today. You don't feel bad if you don't understand it all the first or second or third time through. Just keep at it. For me, it's the metaphor I like is Magic Eye. If you've ever done Magic Eye, it's one of those things where it's a two-dimensional image, but if you stare at it just the right way, eventually your brain interprets it as a three-dimensional image. But at first it can be frustrating until it clicks. And that's sort of how metaprogramming has been for me. So don't feel bad if you don't get it. I've tried several times over the years to get metaprogramming, and I still am not an expert, but I'm feeling more and more comfortable each time I go through it. Just keep going, watching videos. As I said, there are many metaprogramming videos that are really good, and reading blog posts. I'm going to reference a bunch of them down below, so you can sort of read the same things and watch the same videos I have. I'm going to be presenting a whole bunch of those videos in the next talk, but for now I'm going to sort of get us going on real world, some examples in code. Words of warning. First of all, most importantly, you may not need this. If you're getting started in Elixir, you probably don't want to spend a lot of time learning metaprogramming now, because you probably don't need it for several different reasons. First of all, you can go very far with Elixir without deep knowledge of metaprogramming or macros. The same is true of OTP and concurrency. And the reason why, which is a different topic, but they're both special, amazing things that Elixir provides, but you can get the benefits of metaprogramming as well as concurrency because they're baked into the powerful libraries and frameworks. For example, Phoenix, I just give you Phoenix examples here, but Phoenix lets you spin up millions of simultaneous, completely isolated WebSocket connections. And if any of them dies, only one user is affected, whoever's connection that was. Everything is isolated, so any other users who they don't know that another session died. It's completely isolated, which is not true typically in object-oriented programming programs. So that's a benefit you get of OTP, even if you don't know how to use OTP. It also gives you scalability out of the box, so you can run your Phoenix program using all the cores on your CPU or across multiple computers, etc. Phoenix also includes DSLs, one of which I will show you in this talk, or maybe the next one, where it dynamically creates routes through the easy DSL. So you use a simple DSL, you write a relatively terse code, and then Phoenix, when it gets compiled, your code gets compiled into something that's a lot less pleasant to read and understand. It's more verbose, but it is what the compiler is going to work with, or what the actually running program works with. So again, you don't have to understand how the DSL was built using metaprogramming. You get to leverage the DSL just by using Phoenix the way it's documented and intended for you to use. And anytime you find yourself using use, which for example Phoenix does a lot, Ecto also does, you're basically calling a macro, and it is generating a bunch of code for you inside the context where you call use. And again, you don't have to understand how it works to leverage it and to benefit from it. So you don't have to get into metaprogramming now, but it's a good thing to know that these talks exist so that when you do need it, you know where to come. Heeks templates, that's the newer templates that Phoenix provides. That's another powerful DSL. So they basically will change the structure of the language. You don't write standard Elixir in there. You write different things, and it gets compiled through these macros and into more powerful. It allows you to do more in a specific language that's tuned specifically for the purpose of what the Heeks templates are designed for, rather than just using standard Elixir code for everything. which would not be as powerful. Ecto also uses lots of metaprogramming. It's a DSL for writing, for interacting with databases, and not just interacting with databases, for building data structures. My neighbors actually just came into my yard, so I'm going to pause this for a moment. I will be back. How do I stop this? Here we go. Stop recording. I'm back. Okay, so the last point I wanted to make here is that learning metaprogramming requires a brain shift, and for me, that it helps to see lots of examples. I also find use it or lose it totally applies to metaprogramming. I have learned it and then forgotten it, and learned it and forgotten it several times. Basically every 6 to 12 months I try to get back into it, and I feel like I understand it, and then when I come back to it again, I'm confused. It eventually will sink in, but I think until I actually start doing lots of metaprogramming, it won't really sink in. I did about a year and a half ago do a good chunk of metaprogramming. It's the only time I've ever had to do a lot, and I was able to do it fine. But then I came back to it 9 months later or something, and I couldn't remember what I was doing. So the woozle effect, if you know Winnie the Pooh, Piglet and Pooh go in circles hunting a woozle, but the tracks they follow are merely their own. I feel like I keep circling back to becoming a metaprogramming learner. The Krebs cycle is something that I mentioned earlier. Nick Lane, the biochemist who studies sort of the origins of life and the chemistry that might have led to life's arising. He talks a lot about mitochondria and the Krebs cycle. And I thought this was funny in a Twitter post I saw, that the real Krebs cycle, the Krebs cycle is actually a biological thing where you basically extract energy from food and glucose, and it gets turned into various ATPs and through chemical reactions, and there's lots and lots of steps in this big circle. Somebody said the real Krebs cycle is learning the Krebs cycle and then forgetting the Krebs cycle, which I thought was kind of funny. So as I said earlier, I'm not an expert. I've done metaprogramming, but only a tiny fraction as often as the true experts out there have. So I will ramble on and on because metaprogramming is hard to grasp. I find coming from it multiple times from multiple perspectives helps grasp the concepts more fully. And I've also found that organizing this large live book has been very difficult because it doesn't want to work with that much material. So organizing the material in this live book has been sort of difficult. So I will sometimes hit the same topic twice, but I think that's actually not a bad thing because I find that these are complex subjects to understand, and seeing it multiple times from slightly different angles can help. True experts on metaprogramming are people like Jose and Chris McCord. Jose invented metaprogramming in Elixir. It's used in other languages, but he basically built Elixir using metaprogramming. Chris used it extensively to build Phoenix. And this is my friend Wojtek. I had the great pleasure years ago of being a presenter at the same MPEX conference as him, and we got to talking after the conference, and he's a great guy. And at one point, in an earlier version of this talk, I put a photo of Wojtek and my son. Wojtek stayed at my house 1 or 2 nights, and we had a wonderful time, but he and my son were engaged in a very serious ping pong battle. I decided to take that out because I don't have permission from either of them to post the photo. Wojtek and I also played ping pong, and we plan to eventually, after this COVID thing is over, battle again at ping pong. I'm looking forward to that someday. But those are the true experts on metaprogramming. They have done 1,000 times more metaprogramming than I have. And maybe one of these days, these true experts will record a more expert level metaprogramming video or more. I'm not asking them to. It'd be great, but they've given us like years and years and years of their lives and built all this stuff. Thank you so much for everything you've done. Not a request, just a thought that I'm just warning everyone that I'm not an expert. So if I'm not an expert, why am I presenting this? I think this is important to present because many of you may be in similar positions. I've made excuses over the last 7.5 months for why I'm not recording this. First was I didn't know everything, and I don't want to waste people's time. And I eventually realized that, well, if you have some knowledge, that can actually be an advantage. There's something called the curse of knowledge, and the curse of knowledge means basically if you know a subject really, really well, it can be very hard to teach it to somebody who doesn't know it really, really well. So having a little knowledge helps you teach people who have no knowledge, or having an intermediate amount of knowledge helps you teach people who have a sort of beginner's level knowledge. So everyone who's watching this talk knows some things well enough to teach others. Even if you're not an expert, you still have knowledge that you can share with others. Second thing was that I don't know everything, and I don't want to embarrass myself. Most of us suffer from imposter syndrome at one point or another. It's a very real problem. But I realized I know enough to help non-expert metaprogrammers, so that's what I'm doing here today. But don't let perfectionism or imposter syndrome, I keep doing that, prevent you from doing things. Share what you do know with people who can benefit from it. Also, I've been really depressed about the state of the world, rising fascism, global warming, climate collapse, what's going on, Russia's invasion, and war crimes against Ukraine. Just totally depressing. But I can't do much about any of those things. I can give money, I can try to reduce my carbon footprint, etc. But really all I can do is try to make the world a little bit better and make people a little bit happier however I can. So don't cower at the overwhelming size of any challenge. We're all facing these challenges. Do what you can, and others will do what they can, and we'll hopefully all get through this and make the world a better place collectively. Lastly, I've been working on something super cool. I had an series of ideas about a decade ago, and started in on them and then basically set them aside for years. And in the last few years I've been trying to use my weekend and evening time on this sort of side project. It's something I really, really, really want to build, and I think it's very exciting, but finding time when you have a day job and a family is really hard. And then I started this channel as well, so I've been putting more priority on that project than this channel, but it's important to balance your life and avoid going 100% on anything. So I'm here, and there are two tweets that actually got me off my butt to finish this. One was this tweet by Peter Solnika. He said, "I start to feel more and more determined to basically build this thing in Elixir. I still need time to learn more about metaprogramming, though. Maybe just trying to build something, even if I fail, would be a good learning opportunity." So this is somebody who he really wants to contribute something to the Elixir community, but he doesn't feel like he knows enough metaprogramming to do what he wants to do. I was like, God, I should get this thing out the door. Maybe it could help him and other people who are in his situation. And there's this interesting post by, I'm not even going to try to pronounce this woman's name, but I really liked the post. She said, being comfortable with opening up and reading the source code of a library or a tool to understand how something works is truly a game changer. I can't tell you how many times reading the source code has helped me when the documentation was lacking or outdated. And this is one really good reason to learn some metaprogramming. You don't have to learn all the details and intricacies of metaprogramming in Elixir, but Elixir is mostly written in Elixir and is mostly written with metaprogramming. So if you try to understand the source code of Elixir and you don't know metaprogramming, you're going to have a bad time. So learning some metaprogramming will sort of open the door to understanding the source code, which is easy to get to. If you're in the source code for Elixir, not the source code. If you're in the documentation, there's usually a button at the top right side of each function or macro that you can click on. It'll take you straight to the source code for it. It's usually a macro. Occasionally it's like the sort of secret sauce, the sort of stuff that's not written in Elixir. It's written and you can't modify it, but usually it's macros that you can actually see the source code of. Here, and again, this live book is going to be on my ElixirZone GitHub page. You'll be able to get to it. I'll put a link in the show notes. But these are all either Elixir documentation or articles of various kinds that talk about metaprogramming, describe metaprogramming, give examples of metaprogramming. I encourage you to check these sources out. The links will be available. I won't talk about that now. All right, so let's get on to the real show. This is a cool library that I just recently discovered through one of the talks I'll talk about in the next video. But he has built this tool that allows you to... What metaprogramming does is it takes the code that you write and it transforms it into Beam code. there's a whole bunch of, which is what actually runs on your computer. There's a whole bunch of intermediate steps in that process, and it can be hard to see those intermediate steps. What this library does is it allows you to see sort of probably the most interesting intermediate step, which is what basically does your code compile into. So the compiler takes your code and it runs the macros, and then it outputs something which then gets transformed in lots of other ways. But what's that sort of final first step look like? And you can run this command, and I'll show you: mix decompile, and then the name of your module to expanded. And I'm going to provide a couple examples that I did myself here. So the documentation is pretty sparse on this library. I was able to go to a Phoenix app that I had created, and just at the top level of the Phoenix app, I ran this line. And what happened when I just picked out one of the files inside of my, I think I said Elixir dot. I'm actually not sure now. I may have mistyped that, but you take whatever the name. It may actually, now that I think about, this doesn't want to let me do that, but I'm not sure the Elixir dot was there. But it basically run this, and then it generates a new file with this name in the top level directory of my Phoenix project in this case. And when I opened it up, so this is sort of what my source code looked like. So this is the router, this is the Phoenix router file, and there are 118 lines in my source code, and they look like this. They have the standard gets and posts that you are familiar with if you've written a Phoenix app. The compiled routes file had almost 2,200 lines, and they were pretty ugly. But this is what sort of, when you run this, these are macros, and the compiler will take these, it'll call these macros are functions, which basically take in something called AST, which we'll see soon, and return AST. So it's a way of transforming the AST. So AST is sort of the first. We interact with Elixir code. Elixir code, if you call quote on that Elixir code, it transforms it into a format called AST. And then you can manipulate the AST in various ways using macros. And so these are macro calls, and they get transformed into basically into various forms of AST, which then get manipulated further and turned into your actual code. But before the later steps of the process happen, it ends up in something like this format. So here, this is a single get. Earlier, each of these gets is a single line. This is the user's register get function, and it has more stuff than I wrote. I wouldn't want to have to write all this. I wouldn't have to debug this stuff. But under the covers, this is all happening through the magic of macros. And again, it's a 20x. The compiled file is 20 times larger than the source file. I did a second example. I have this is an Ecto-based module, and I looked at it. My source code had 711 lines, many of which were comments and docs and examples. The compiled file was twice as large, so it wasn't expanded as much. But you can see you wouldn't want to have to write this sort of thing. But the macros do that for you, so you don't have to sweat the details. You can operate at this higher level of abstraction. You just write this function, and then it generates this code for you under the covers. So let's play around with this. The first example that I made myself. So I created this module called unless true, and inside of it there's just a macro. I'm creating my own unless. This is a macro, not a function. One big difference is if I made this an ordinary function, the arguments that get passed into the function get evaluated every time you run the function. So both Boolean expression and false case would always run, and that sort of defeats the purpose of unless. So if or unless, both of them, you only want to run the case some of the time. You don't always want to run this. So if this said like fire the missiles, you may not want to fire the missiles, but if you make this an ordinary function, you're always going to be firing the missiles, because that's just how functions work. They evaluate their arguments. So instead, we can use a macro, and then these things don't get passed in. They don't get evaluated and passed in as values, which is what happens in an ordinary function. whatever gets passed in is passed in as AST, and we'll see what AST is shortly. But AST is like, it's not executed. That's sort of the key point. So this code, these two values that get passed in, they're AST, they're not evaluated. They're sort of data structures or something that representing code that could run. And then in here, what we're doing is, so the quote block is basically taking whatever's inside of it. So this is the stuff that's inside of it. Whatever's inside of it, it's expecting to be sort of ordinary Elixir code, and then it's going to transform it back into AST. That's what the quote block here is doing, is it's taking the Elixir code inside, transforming it back into AST, because that's what macros do. They take in AST, so this has to be valid AST, this has to be valid AST, and then everything here has to be valid Elixir. And that's why we call unquote here. Unquote is a way to take the AST and turn it into basically Elixir code again. So the thing I highlighted is going to be Elixir code. False case again is AST, but when I unquote it, that becomes Elixir code. And once both of those things are Elixir code, then this whole function, this whole expression here is Elixir code. It's not AST anymore because we've unquoted the two AST pieces of AST. I think this bang operator, as we'll see later in this talk, is a macro, and the if operator is also a macro. So these are, and they're Elixir macros, so it's a valid Elixir code. It happens to be a macro, and they will get expanded through something called macro expansion. But everything here is valid Elixir code. I guess, and I said earlier, Elixir is largely written as a whole pile of Elixir macros. So we're calling multiple macros here, but the bottom line is we're passing in unevaluated code in the form of AST here. We're passing the AST into this. We're unquoting it to turn it into standard Elixir, and then this whole line becomes Elixir code, and then the quote block takes the Elixir code and transforms it back to AST. So we're passing in AST and we're returning AST, because so that's what this is doing. And the AST that gets returned looks like this. This is actually the AST. AST you will always see as three-element tuples. So the first element here, actually I'm saying always as three-element tuples. This is not a three-element tuple. I'm actually confused by that. I've seen this a couple times. I don't know what's going on here. Let's pretend that didn't happen. Yeah, because that's one thing, two things, three things, and four things. I don't understand that, but okay. So calling this macro from another module modifies the compiled code. Right, so this is my source code here. I create another function, and because I want to separate out the compilation, I'm not doing that within the livebook. The livebook makes it hard to compile without actually running the code. So I created a file, which is, you'll find in the directory on my GitHub, inside the metaprogramming directory within my GitHub for ElixirZone for this episode. So I created a module, which I named obviously true. Require, whenever you see require, you're basically requiring another module. And whenever you want to use macros in a module, as opposed to functions, you must call require. If you've ever had, this often happens if you're working like Ecto or something, where you use the Ecto code somewhere down here, but you don't require, it'll say you must require it if you want to use it. That is the case with macros. So unless true here, which is this here, I defined as a module with macros in it. So that's why I'm requiring it. I'm saying I want access to the functions and the macros inside of unless true. If I didn't, it wouldn't work. So then I defined a function, do the thing, and I'm calling this macro unless true dot unless. So I'm going to call this function, this macro, and as I said earlier, these they're going to get passed in as AST. So the first thing that's going to get passed in is the value true, and the second, then there's a do block, which will get passed in as AST as well, which is just the atom fire the missiles. Then using this wonderful library, which I mentioned here earlier, decompile, I decompiled the compiled code. When you call, oops, where did I go? When I compile, I use decompile to see what the compiled version of this function module is, this is what it returns to me, which is a little ugly, but it's easy to evaluate. So the first thing to notice is it will start inside this parenthesized case. Case true, return false. So this everything in the parentheses is just going to execute as false. So then case false do, that's going to evaluate to nil. So everything inside the definition of this function is going to when you execute it, is going to return the value nil. Since we don't pass any values in, we're always going to return nil. Everything in here is going to always evaluate to nil. But that's the key point, is that the AST that gets passed in does not get evaluated. So when the code gets compiled, again, this is the code that I wrote. I called this function, I called this macro, and I passed in these values. My code, basically the macro, executing this macro replaces the macro call with everything inside of the function here. So this case, everything from case to this end here, is what gets what replaces this macro call. Now we can see that whenever you call this function, it's always going to return nil, but the compiler doesn't try to figure that out. There may be something later in the compilation process that does try to find this optimization, but the point is that typically the compiler just puts in AST here. It puts in sort of code. It doesn't try to evaluate your code. And you can see why that's helpful in the second case, which is here. I'm taking the same, I'm calling it possibly true. It's basically, I'm requiring the same macro, I'm calling the same macro, but this time I'm calling it not with the Boolean value of true, but with a variable. So I'm passing it, the function now is going to take a variable, true or false, which, you know, the compiler has no idea what that is. It could be a function, it could be it could be an atom, it could be a Boolean. It has no idea what this is, but whatever it is, it's not going to execute it. It's just going to pass it in as AST into the unless, which is up here. Sorry, it's going to pass it in here. So true or false. So again, it's going to, this is going to be the final code which gets injected in, and in this case, this is what when I decompile this function, this module, I get this. So now we can evaluate this. So again, the true or false, if we pass in true, it will then match. Here it's looking for a value of false or nil, which is not the case if I pass in true. So it's always going to return false here, and then case false do gives nil. So again, it's going to be the same outcome as before, but if we pass in false, this line will match here, and it will return true. So this will become case true do, and true is fire the missiles. So calling this function with the value of, what did I say, false or nil, will result in the atom fire the missiles getting returned here. So this code in here does not execute at compile time, it executes at runtime, as did this code here. Even though we can see that you could cut this down, simplify this to just nil, because it's always going to execute as nil, it doesn't actually try to do this. It just takes this code, which you wrote, transforms it to this code, which is what it will actually execute at runtime. Similarly here, this is in the other case where I pass a variable in, this is what it will actually execute at runtime. And we can see that here. So I opened up an IEx session, and I compiled the possibly true library module, and then I called it with a value of true, and it got nil, and false, I got fire the missiles. Let's look at Elixir. Elixir has lots and lots of modules. So one bunch of them is in kernel. So if you do Kernel.info macros, you'll see all these things. So def, for example, is a macro. The new debug, which just came out in, I think, Elixir 1.14, that's also a macro. There are many, many, many macros. So many, or is a macro, match is a macro, is struct, which we will cover later in this talk, actually. Similarly, there's something else called kernel special forms. In a talk I gave last year or earlier this year, I wasn't actually sure what special forms was. I do now. So these are things you can see in the code, the description here. The basic building blocks of Elixir, they cannot be overridden by the developer. So these are things where you're sort of touching the metal, as one of the talks that I watched described it. You can't actually, when you look at the source code, it doesn't tell you what's actually going on because it's written in something other than Elixir itself. Many macros are written in Elixir, but anything in special forms is not written in Elixir. It's just stuff that is provided for us and treated as magic. We don't have any ability to control anything there. But again, you'll see there are many macros that you can use. With is a macro, require is a macro, quote is a macro, import is a macro. So macros are everywhere in Elixir. This has nothing to do with metaprogramming, but I want to point this out because it's confusing to many people. When you say kernel, so the kernel module is named kernel. This is exactly the same thing as saying elixir.kernel. And elixir.kernel is exactly the same as the atom : quote elixir.kernel. And this is something Jose came up with. I think all atoms in Erlang, all module names in Erlang have to be atoms. So this is the way all Elixir module names appear in Erlang itself. But there's sort of syntactic sugar that allows us to write just kernel or elixir.kernel, and it means it gets treated exactly the same way. I've taken some macros from the Elixir source code and simplified them down a bit so we can sort of get a sense of what they do. So the first one I'm going to cover is this bang operator. So the bang operator, what it does here is it takes the value. Oops, why am I doing that? It takes the value and it unquotes it. Again, so there's a quote block here, which means we're going to be passing in value as AST, not as the value itself. It's getting passed in as AST. To turn it into Elixir code, we're unquoting it. So we're taking the AST, we're turning it into Elixir code. So then we can evaluate it at runtime, so quote's going to return AST, but at runtime it's going to evaluate the AST. So at this point it's going to say case and then the actual value. So this might be X. If we're passing in the Elixir value X, this whole thing would become case X do, or whatever. Actually, the X is a bad example because that's what the code is. Let's say it's Y, whatever. So whenever the value is false or nil, this is going to return true, and otherwise it's going to return false. So that's what this is doing. This is defining the bang operator as a macro, and it is saying, okay, take the AST of the value, transform it into ordinary Elixir code, then do a case. If the value is false or nil, return true, and otherwise return false. This is another macro defined, which is it's similar, but it's basically saying if you have a double bang operator, so a bang on top of another bang. So this is the way that you would represent in AST the bang value. Bang value in AST looks like this, and we'll see why shortly, and see many other examples of AST. But this is saying if you basically have a double bang operator in front of a value, what are we going to do? So again, we're taking in value as AST, we're unquoting it to turn it into ordinary Elixir, we're then evaluating it and looking to see whether it's false or nil, in which case we return false, which is the opposite of up here, which is what you would expect if you do a double bang as opposed to a single bang. And if the value is true, then we return true. So the double bang, when the value is true, evaluates to true. When it evaluates to false or nil, it's false, and when it doesn't evaluate to false or nil, then it's true. So that's a double bang, and you can see this in the Elixir source code. This is a slightly simplified version. Here's if, again, a slightly simplified version of if from the macros defined in the Elixir source code. So we're taking in a condition and we're taking in clauses. Clauses here can take a keyword list. It can be a keyword list, which is what we'd expect. If you provide a do-else block or just a do block, the clauses will evaluate to. This is one way to write a keyword list. The first key is :do, and the second key is :else, and the values are there obviously. So if you build a if if you call if, you're calling a macro. If you pass a do block, you will end up here, and it will add in an else block for you, which just returns nil, and then you'll end up down here regardless. And then this is where the magic is really happening, because this is calling build if. So here you have a condition, you have a do block, and you have an else block, and all these things are going to get passed in as AST, not as Elixir. And again, we have the quote block, which means we're going to expect Elixir in here, but we're going to transform it back into AST. So this is taking in AST values and returning AST. That's what macros do. So in this case, we're going to take the condition and we're going to unquote it. Now, again, the compiled version of your code will not execute this. It will just build, so you will end up with a case statement in your compiled code, and then at runtime, it will actually evaluate this. But that's why we're working with AST. We don't evaluate it when we call the macro. The macro transforms the code, and then that code that the post-transform code gets executed at runtime. So in this case, so we're going to take the condition at runtime. We'll end up evaluating it. At compile time, we're just going to simply end up with, we're going to place the code with just a case do end with the stuff in between that looks roughly like this, just with the value of unquote else clause replaced by the Elixir version of the AST that gets passed in here, and similarly the do clause would go here. It would this would get passed in as AST. It would get transformed into Elixir code here, but it wouldn't get evaluated until runtime. So that's how Elixir's if function macro works. It's not a function. If it were a function, when you called if, it would evaluate both inputs immediately, and that's not what we want. We want to defer execution until runtime. So that's why we work with AST here. AST does not get evaluated at compilation time. It just gets manipulated. Okay, so I keep talking about this thing called AST. What the hell is it? I have not been... probably should have started here, but here we go. So many values have the same representation in AST as they do in Elixir itself. 33, or any sort of number, is an example of this. Numbers, when you quote them, this quote do, I could also write as quote do, let's see if we can end. It's the same exact thing. It's going to work exactly the same way. When you do that, when you quote a number, it just returns you the number. So that's valid AST as is. Strings also are valid AST. Atoms are also valid AST, so you don't have to transform these in any way. Lists are also valid AST. Two-element tuples are also valid AST. Not all tuples are any tuple longer than 2 elements is not valid AST, and I'll explain later why 2-element tuples are treated differently. So here are some things that don't get passed through to AST unmodified from Elixir code. So here we have a map with 2 keys and values. When you quote this to basically take the Elixir code and the Elixir value and transform it into AST, you get back something different. I said earlier, AST is always a 3-element tuple, and I then immediately showed an example where that wasn't the case, which confuses me, but here you can see it's a 3-element tuple. It's basically defining the function here, which is the % sign and the braces, which represents a function to create a map, and then the this here is sort of, it's considered the context, or the meta. I don't know. Let's call it the context for now. Usually you can ignore what's in here, but yeah, these are the arguments here. The third is a list of arguments, and so you can see how this sort of looks like this. But in our Elixir code, we can use this pretty data structure, but in AST you can't directly use this this data structure, because it's not valid AST. This is valid AST down here. So you can transform back and forth. We'll have lots of examples of that soon. A 3-element tuple, as I mentioned earlier, also similar to the map function. It also has its own, here it's just braces without the % sign. This is saying the function is these braces, which is to make a tuple, and there's 3 arguments in the list of arguments. The variable x is represented in AST as this tuple. It's just saying it's an Elixir variable named x. That's what that's saying. Here we're saying, okay, pizza, which is a module name, let's say, it gets represented this way. It doesn't as an alias. It's just saying it's pizza. I don't understand all the details here, but it doesn't really matter. If you stare at this, you get familiar with it, and that's what matters. You can also take a module, a full module, and this transform it into AST, which is what this is. This is the def module at the top here. This piece here is the second argument, and then this is the list of arguments. This is the sort of metadata here, and this is the list of arguments. The list of arguments itself starts with aliases, but what's really key here is that it's an empty block. You can see here that it's a block with no attribute, no parameters. Here it's a function we're going to transform into AST. There's a def. You can see the value here, so that the body of the block is this is just 7. Again, you don't have to understand these details, but it's key. It's important to understand that AST looks different from ordinary Elixir code, and to have a sense of what the AST looks like. So here we're saying true and false. I'm going to transform that into Elixir, into AST from Elixir. It's going to call the and function with 2 values, true and false. So true and false, and is an infix operator, which gets transformed as AST into basically a function call and on 2 values, true and false. We saw earlier the source code for the bang operator, which is basically going to turn the true into a false. But again, it doesn't just say false. It doesn't evaluate this code. It simply transforms the code into AST from Elixir. So we know that bang true is equal to false, but the compiler doesn't execute it. It doesn't simplify it. It just says, okay, I need to transform this Elixir code into, what did I just do? I don't know what I just did. Oh, I didn't want to do that, sorry. We're going to transform the Elixir code into AST. And this is the AST representation of the bang function, or I guess it's a macro in this case, but the bang with a single parameter of true. And we know that's going to evaluate at runtime to false, but the compiler doesn't do that. It just returns us AST representing exactly what we gave it as Elixir. Similarly, x in 1 and 2, it just transforms that into an in function call with the values of 1 and 2. X equals 8. So this is beginning something called macro hygiene. Basically, sorry, it's not a macro, but sorry, I'm getting ahead of myself. So we define the value of 8 here. We might expect x in 1 and 2, in the list 1 and 2, to return false. Again, if you evaluated this code at runtime, it would give you that. But in this case, these are totally independent things. We're saying, okay, let's assign the value of 8 to a variable called x. And then we're saying, okay, here's some code, x in 1 and 2. Now just give me the AST representation of that code. We're not asking it to run the code, execute the code at all. We're just saying, give me the AST representation of x in 1 or 2. And then again, it's the in function call. And you can see there's 2 values here. One is the variable x. This is the AST representation of the variable x in Elixir. And then the second argument is a 2-element list, 1 and 2. So this is the AST representation of this. And since Elixir always returns the value of the last thing, it doesn't return x equals 8. It doesn't return 8 to us. It returns us the value of this AST. If we actually wanted to evaluate this, how could we do it? So again, let's try setting x to 8, and then we're going to do the quote do. This is the same as what I showed before. This piece here is simply going to return us the AST representing whether or not the variable x is in the list 1 or 2. And then I'm going to say evaluate quoted x2, and it's going to say, I don't know what the hell you're talking about. There's no such thing as x. And we can see there's an x here, and I even provide another x here, but this code here does not specify how or where x might come from. So we can't evaluate this code because this AST has no representation of x within it. This is like another world that this code here, the AST here, does not see this, and it also does not see this. So we need to tell it somehow that it's allowed to look. And that's what this unquote here is going to do. It's going to allow us to look at the value of x. So here it's going to say, okay, so what we're doing here is we're saying, okay, give us the AST representing whether x is in 1 or 2. But in this case, I want you to reach out and grab the value of x when you're writing this. So here what we're actually going to be doing is we're going to be grabbing the value of 8 here. And then we're going to be in the AST of whether 8 is in 1 or 2. And then we're going to say evaluate the quoted. So quoted is another way of saying AST. Anything quoted code is the same as AST. So evaluate the AST is basically what this is saying. And when you do code eval quoted, the value is returned as the first element in the tuple, and then any variables in the context of that evaluation would show up here. We'll see examples of that later, but in this case there are none. So is 8 in 1 or 2? No, it's not. So it's going to return false. So here's another way that we might do it, where if we want to pass in a separate context, so we don't want to reach outside of the into just the sort of the code that existed when the AST is defined. We instead want to use a specific context. We can pass that context in when we call eval quoted or eval AST, and in this case it's going to use the value of x equals 2. And this is using the var bang. Is var bang I want to say function? I'm not sure if it's a macro, or it's probably a macro. But in this case, we're going to explicitly say var bang is saying it's okay to reach outside of my context and grab the actual value of x. And using var bang, we can also even change the external value of x. But by default, if you don't use var bang or unquote, it won't allow you to reach outside the context of the AST. So these are ways of, this is called something hygienic macros. You have to explicitly say it's okay to reach outside of the context of the AST. Which is what the var is doing here. And in this case, it's returning true as the value. So it's saying, is the value of 2 in 1 or 2? Yes, it is. So true. And then it's saying that, well, the context I used to evaluate this had a value of 2 for the variable x. So that's what that second piece of the tuple is saying. I sort of described this earlier, so I'll skip this. So there's something called Macro.expand, and you have to provide it 2 things. You have to provide an AST, which we're passing in through the pipe operator here, and the second thing is you have to pass in an environment. The double underscore env is the current environment. So you're basically saying evaluate the AST returned by this quote statement in the context of the current environment. Well, actually, it's not saying evaluate, it's saying expand this. So this is not actually execute, it's not evaluating it, it's just it's expanding the macro, means taking the AST and recursively looping through, looking for any macros within the AST and calling those macros recursively until there are no more macros that can be expanded. And what you end up with is a big ugly mess here, which you can understand if you stare at it for a while, but it's ugly, it's confusing. Compiler knows what to do with this. I don't really know what to do with it, but it doesn't matter. The point is, this is what is happening in your code. You're saying if true, do 1, else 0. We're quoting it, which means we're turning it into AST, and then we're expanding it, which means we're basically, so if itself is a macro, we're going to get rid of if, because the macro is going to get expanded into this case. And so you don't see, there's no if here, because if is a macro written in Elixir, which gets transformed into something else, which is a case statement. So again, this is not executing our code, it's not evaluating our code, it's simply taking our AST and repeatedly expanding it to the fully expanded form, which then will continue on the compilation process and will be executed when it's called, but that's separate from the compilation process. Here's another example. I won't belabor it, but you can see there's a lot of stuff getting generated here. I'm not going to go into the details, they're not important. So I promised earlier to explain why two-element tuples don't get modified. It's because keyword lists are much easier to read when they can be displayed in a nice clean way like here. So this is a keyword list. It's a list of key value pairs. Under the covers it actually looks like this, but we can display it like this. It's super clean and simple. You can even remove the brackets from this and display it. Just list a bunch of key value pairs like this. Is super clean, and they wanted to keep the AST looking super clean like that, which is why two-element tuples have a special way of doing it. Otherwise we'd have to do something like this is ugly here. Manipulating this AST is really ugly, whereas this is totally valid AST here, and it's nice and clean and easy to read. Eval quoted, I have been giving examples of that before. I mentioned earlier that so it will evaluate here 17 plus 18, give you the value, and this is the sort of context. I won't belabor that, we've been through it. There's nothing string to quoted, so this is in the code module. You'll see we've been looking at the module. We've been looking at now we're looking at the code module. So here I'm taking a string and I'm transforming it into quoted, meaning AST. So this is the AST representation of the string 17, but it's not really, because it's an integer. Because we passed in a string and we said, okay, we want to take the string that we're inputting and turn it into AST. The string has the integer 17 in there, so it transforms it into AST 17. So how could we transform this into a string 17 if we wanted to do that? In order to do that, we could take a different 17. Within the string, we could pass 17 into integer to string, which will turn. So the integer will get turned into a string to quoted, and then we take the value, and we can see that it actually returned here. This is a better way to do it. So we take this long string, we turn it into AST. We take the first element, which I did here, and you quote. This is you evaluate the AST, take the first element, and now we have the string 17. Separate way to do this would be to pass in a string to quoted, but to explicitly quote the 17 within the string itself. So that gives you the same value. There's something called Macro.string, which is very, very cool and useful for evaluating when you're working with AST and you want to see what it looks like. So here I take the 17 integer to string, turn it into AST, take the first value, which is the AST itself. Now if I want to see what the AST looks like, I can call Macro.string. We know that the AST itself is kind of ugly, so it looks like something like this. This is actually what we have here. So string to quoted on 17. This string returns this ugly thing, which is hard to see at first glance what it's doing. But if you call this magic Macro.string, it will then transform the AST, this ugly stuff here, hard for humans to grasp, back into a string, which you can then see, oh yeah, I recognize that. It's much easier to recognize it there than it is here. This is the same thing. You can see here the integer to string, and you can see the 17 all the information in the pipe operator, but if you call macro to string, it'll give you a string representation of your AST. Similarly, the example earlier where we passed a string that had a string within it, we turned it into AST, which is what this line's doing. If you want to see the string representation of the AST itself, we can see it right there. We've used quote. Let's talk more deeply about what quote's actually doing. So it transforms Elixir code into its AST representation, as we've said before. It's in kernel special forms, and it returns. So the 3 plus 4, the plus operator is an infix operator. So this is basically calling the plus. I mentioned earlier that this metadata here, or context, we can usually ignore it, but in this case you can see that it's saying that the kernel function is coming, the plus function is coming from the kernel module. So we didn't have to, luckily we don't have to spell out kernel.plus, etc. here, and it gives us the syntactic sugar that we can say 3 plus 4 rather than kernel.plus 3, 4. But that's what the AST representation is effectively doing. It's turning it into it's saying that the plus operator is from the kernel module, and it's taking 2 parameters, 3 and 4. So again, it doesn't evaluate this as 7. It just returns AST representing the operation 3 plus 4. If we want to see the string representation of this AST, we just call macro to string and we see it. There's also macro to string, and then string to quoted. So you can go back and forth however many times you want. It's just, there are ways to go back and forth between different representations of your code. Metaprogramming is code that writes other code. Manipulating AST lets us interact with the code generation process in ways that most languages don't allow. Logger is a good example of this in Elixir. At compile time, logger calls can actually completely remove the debugging code. If let's say you're at a certain log level, you say, and we'll see an example of this later, but if you say log level info and you have a call to logger warn, that will get compiled in your code. But if you did the opposite way, you said your log level is warn and you make a call to logger.info, it will say, oh, logger.info is a lower level call than logger.warn, and it will just not even compile your logger.info call into your code. So your compiled code will not even have the line in there. Your source code has it, but your compiler will just ignore it. That's the sort of thing you can do with macros. You can also define new language primitives that are missing from Elixir, like while. And much of Elixir itself is built as macros. So typically it's a 3-element tuple, the function call, the context, and the argument, a list of arguments. Again, I occasionally look at stuff and it doesn't seem to have that shape, but I've heard that all AST has this shape, so I'm a little confused by that. But and then there's the syntactic sugar of 17 plus 18 being the same as kernel dot. Actually, that should not say multiply. That should be addition. The typo there. Sorry. And the context is elixir.kernel. So the context. So the kernel is saying the module, and the module is in the context of Elixir. So the full module name, I guess, is elixir.kernel here. And we've seen examples of this stuff. So another aside here, because when I did my first example of this, it came out weird, and I thought if anyone else hits this, you should understand this. So I was doing some lists, and if you do lists, Elixir will try to help you out by saying, oh, you didn't actually mean a list of integers. What you actually meant was this, you meant to say cat. And this is not a cat string. This is a cat, what do they call it? Shit, I have it down below. I can't remember what it's called. Character list. So character list comes from Erlang. Erlang didn't originally have strings, it used character lists. Now Elixir strings are all UTF-8 and everything, and it's nice and simple. But if you have to interoperate with Erlang, you often have to use character lists or char lists. And Elixir will, if you have a list of numbers that all can be represent potentially characters, it will try to be helpful, and instead of displaying it as a list, it will display a string-like thing, which is actually a char list, not a string. But that's what's going on here. It is a list. It actually is a list, and you can transform it explicitly into a char list. You can also transform it explicitly into a string. So here you'll see that we're double quoting it. Up here, the char lists have single quotes, and so you always have to be careful that in Elixir that if you want a string, you want to use double quotes, not single quotes. Single quotes represent char lists, which are only there, I think, because of Erlang, but it can be very confusing. So there's another operator that you can use. Let's say you want to get the number representing the character A. You can put a question mark in front of it. Certainly capital A, you can get the integer mapping to the capital A. There's also special characters like escaped characters here, and you can get the character codes. So the original example that I was trying to do was I was trying to add 7 and 8, I think, and it gave me this very strange output, and I didn't want other people to hit this and be confused as well. So that's why I'm going on this aside here. The 7 is this character, and 8 is this character. And character lists are not the same thing as strings. They're totally different. You can transform them using the functions I just mentioned. But also if you turn them into AST, so 7 plus 8 here is exactly the same thing as this character list with the plus operator. If you use numbers that are not matching characters, it will just give you an ordinary list. It will display it as an ordinary list. Here, to show you what's going on, this is not a list. This is a tuple, but this is giving us the numbers that are representing each of these letters. And so then if I make a list with those exact numbers, it will then return a character list. It will display as a character list. It's not actually, it's just a list of numbers, but it's getting displayed helpfully as a character list for us. And you can transform it explicitly to a string if you want. Okay, enough of this. Been through this. Oh, there is one nice thing that you should know about in IEx. There's an info.info function, and if you're ever confused what something is, you can just pipe the data structure into info.info, and it will tell you a lot of stuff. So here it's telling us this is a string. It's a binary. It's string. You can see the raw representation of it as well. 101, 102, 103. And it'll tell you that this here is not a string, it is a list. It will also say this is a list of integers that is printed as a sequence of characters. So this can be quite helpful, this IEx.Info.info. And here it's saying this is just an ordinary list, nothing special about this. Unquote, we've seen a lot. There's something else called unquote splicing that you might want to use in rare occasions. You should know what it is. The difference is if you call unquote on this Z, it will stick the actual array or the list inside of the other list. So you have a list inside a list. If that's not what you intend, if you actually just want to take the elements and add them to this list, you can say unquote splicing, and it will splice the values into the list at the location specified. We've seen macro-to-string. It's helpful. Just more examples of that. This is taking AST. I'm not sure what. Yeah, so this is very hard to grok. If you have AST and you want to know what it is, again, you can just pass it to macro-to-string, and it'll give you a string representation of what you're trying to do. Also, again, so this stuff gets lazily evaluated. So everything inside this quote block is returned as AST. It does not get evaluated. So you can just put in random things here that don't have to exist in your code anywhere. At runtime, they'd better exist in your code or you're going to get runtime errors. But at compilation time, it's totally valid to just put in variable names that don't exist into your AST. And because the AST doesn't get evaluated, it will just get transformed into code. And if we want to look at what the code looks like, this is just an operation. It's saying, okay, get these 3 values, and then map over them and add 1 to each of them. So it's obviously expecting these 3 things to be numbers, but it doesn't get evaluated. The AST just is AST. That's all it is. Similarly here, we haven't defined X, Y, and Z. We just say, okay, I want to define the operation X times Y times Z, and it gives us the AST representing that operation. This can get deeply nested. This is just a series of addition functions, and you can see it looks like the pyramid of doom in JavaScript or something, but that's totally fine. Elixir, the Beam compiler, is totally able to handle this. Our codes actually become massively nested AST, and the Beam compiler goes and is able to execute that for us without any trouble. It's perfectly happy to deal with these data structures, which to my eyes look horrible. And you probably wouldn't want to work with this every day. This representation is much nicer, and so thank you, Jose, for allowing us to write this nice clean code and still have the ability to interact with this as necessary. So macro hygiene I mentioned earlier. So here we're returning the AST representing the variable X. This is what the AST looks like. Anything outside of quote is invisible inside a quote. So the fact that this is 3 is irrelevant here. We're just returning the value of the AST of X, which is just the value of X, whatever X is, but it's not replacing that value with 3. If you want to explicitly pull values in from outside of quote, you need to unquote, and then it will pull the value in from outside the AST at compile time. Similarly here, we're pulling in the value, so this is just transforming into 7. So the value of the AST is 7. 7 is represented identically in Elixir code and in AST, so we just get 7 here. To pull in values at runtime, you can use var. So here we're saying, okay, I want you to grab the external value of X, and we're evaluating quoted, so we're going to pull the value from the context we're passing in here, which is that X is equal to 17. So it gives us it says the AST is 17, and this is the context. Critically, even though we have done this we have not transformed the value of X outside of the AST itself. So if we then say, what is the value of X? It's not 17, it's 3, because I think earlier we defined it as 3. So this does not change the value of X. We could change the value of X by assigning to var X, but we didn't do that here. Let's see if we do it. I think soon we'll do it. Here we define 2 values, and we're going to pull them both in using unquote twice. So just talking through this one more time. So we're pulling in the value. So this is going to get replaced with the value with just 3, and then the plus operator, and then 4. So it's 3 plus 4. We don't evaluate it. We just return the AST. So it's a plus operator and the 3 and the 4. Here we're going to evaluate it and get the first element of the tuple. So here we actually evaluated it. In this case, we're going to do some manipulation. We're going to say, okay, X is 3, Y is 4. We're then going to pull the values in from the outside the AST. We're then going to say X is equal to X squared, so it'll be 9, and Y will be 4 squared, 16, and then we're going to return the value of 9 plus 14 of 16, and it's 25. We're going to evaluate it. We're going to get the first element, which is the return value so it's X plus Y. We've transformed X and Y, so it's 25 is the return value. But critically, it's like Vegas. What happens inside quote stays inside quote. So X and Y are still 3 and 4. They have not changed. Inside of the AST, they changed, but the AST did not change the external environment. It pulled the values in from the external environment using unquote, but it didn't transform the values outside of its environment. So there's still 3 and 4. So if we see, I just put them in a map just so we could see them. The value of x is still 3, the value of y is still 4. If we want to transform values, we can use this, we can assign to var. So that's what we're going to do here. So what we're doing here is we're defining a macro called mult, and multiply takes an x and a y. We're going to define, so this is going to be Elixir code in here. Once it gets quoted, it'll be AST. These values are going to get passed in as AST. So we're passing in value, x and y are going to get passed in as AST, and the return value of this macro is going to be AST, of calling the macro is going to be AST. So what's going to happen inside? So we're going to grab the, we're going to take the AST and transform it into ordinary Elixir. So this is going to turn into 3 times 3. And here we're using var bang of x. So we're going to say that we're going to modify the external representation of x to be 3 times 3, which is 9, obviously. And here we're going to pull in the external value of y, which is 4. So this is going to be 4 times 4, 16, and we're going to assign that to y. So we're actually transforming the value externally of y to 16. And then we're going to return the sum of those two, which is 25. So again, we don't execute it initially, but if we evaluate it, we're executing it. So we're returning the value 25, but because we've now executed it, we can see that when we look at what x and y are, they have been transformed. And so that's the key here, is that because we did var, so we unquote to pull the values in, and then we reassigned the value of x here when we said var bang x equals, and we reassigned the value of y when we said var bang y. So we've actually transformed the external environment. And this is breaking hygiene. By default, macros are hygienic, meaning they don't mess around with the external environment. But if you explicitly want to mess around with the external environment, you can do var bang and assign to it, and you will mess around with modify the external environment. There's another very important thing called bind quoted, which is typically used instead of quote. There's several advantages. One is that every time you call unquote, the AST gets evaluated. You may very well not want to do that. If you, for example, in the example above, you can see we unquoted x twice and we unquoted y twice. In this case, it really doesn't matter. It's not as efficient, but the real problem is that x, instead of just being a value, it could say IO inspects or something like that. And every time you call unquote on it, it will evaluate it and it will output something if it has an IO inspects in there or something. So you really only want to evaluate once. Or if it was like a database lookup, you don't want to make the same database call multiple times. Or if it had side effects in it, etc. There's a lot of reasons why. So typically we should use bind quoted, and what this is doing is it's taking the AST that gets passed in and transforming it into basically Elixir code, so we can just write it as X now, because everything inside of this needs to look like Elixir code, and then quote will transform it back into AST. So bind quoted is a way to bind variables from the external environment and use them within the Elixir code that gets transformed back into AST. You can see it in use here. Not sure. Let's see. Macro.escape for values. Okay, so we saw a 3-element tuple. So this has a different representation. This is the Elixir representation. This is the AST representation. If you want to pull in the value from an external environment, you need to do something called Macro.escape, and let's explain why. So let's assign this tuple to a variable called this val. If you quote this val, you're saying I want the AST that gets returned has nothing. It doesn't look at the value at all. All it does is gets the it says this is a variable in Elixir called this val. That's all it is. So the fact that you assigned a value to it is ignored by the AST here. If you actually want the value that is assigned to this val, unquote will work for data structures that have the same representation in AST and in Elixir. But a 3-element tuple and many other things like maps and structs do not have the same representation in Elixir as they do in AST. And so in those cases, if you want the value of this val, you need to call Macro.escape on it. So again, this val, we said it's this 3-element tuple. If we call Macro.escape, it transforms it into an AST representation, a valid AST representation of that data structure. So here, if we do so, we unquote the Macro.escaped version of the value. It works out properly. That's why you need to call Macro.escape. Here's an example. If I uncommented this, it would fail. The reason it would fail is because tuple here is a 3-element tuple, and if I just unquote it, that is not valid AST. That's why you have to call Macro.escape on the tuple to transform it into the AST representation of the tuple. Then you can unquote that. You could also put the Macro.escape call inside of the unquote. The key is, if the data structure does not have the same representation in AST, in order to pull in the value of that variable, you must escape it with Macro.escape. Kernel is struct. I want to work through a more complicated example here of a macro that's in the kernel module called isStruct. Before I do, I want to talk about what structs are, how they look. We'll build one up, and then we'll be able to look at isStruct and understand how the actual source code for isStruct works. I defined a struct with two values, name and age. So they must have values, and I defined a type for them. This isn't important, just defining the module, the struct. Struct is sort of a souped up map, and that's why we're going to be able to. The difference between map and struct is important for understanding how the isStruct macro works. So we're going to build that up here. So we're going to build a human. Give her a name and an age, and we see the representation of the human. We assign her to the variable Mary. We can inspect it. If you say inspect with structs false, it will show you sort of the underlying representation of that map, which Elixir prettifies the display of it this way, but under the covers it's sort of doing this thing. So there's a double underscore struct with a value being the name of your struct. But again, it displays this way unless you explicitly say IO-inspect structs false. If we get the AST representation of this, we get this. Again, if we just do AST of the struct, of the name rather than the value, it's going to just say it's just the name of Mary. So the fact that we assigned a value to Mary is going to be ignored by this AST that's generated by this quote here. What we want to do is we want to get the value of Mary, so we need to escape Mary to get a valid AST representation of Mary. So in this case, you'll see it's a map operator or map function, and the parameter list has the two parameters that I defined, age and name, but it also has this third sort of hidden parameter, which is struct, which has a value equal to the name of the struct that I defined earlier. So, and we can take that definition and quote it as well. Just these are examples that aren't too important, but if we Macro.escape the value and then we unquote it, we get this. So now we can get into the source code definition of isStruct. It looks like this. You pass it any term. Term is a name in Elixir that just means any value, any data structure. It could be anything. So in this case, term. What we're going to do 3 checks. There's an and here and an and here. So we're going to say, is the term a map? Is there a key double underscore struct? And if within the term, within whatever data structure we're looking at. And you'll notice this is calling the Erlang isMap key function. So Erlang, this is the Erlang module It's an Erlang module, not an Elixir module. And you can use Erlang code within Elixir. And then the third thing it's going to check is whether it's an atom. So it's going to say get struct is the value of struct. It's going to say is there a map? Is it a map? Is there a key within the map called _struct? And is the value of the key associated with the _struct, is it an atom? And we saw earlier, I taught earlier in this talk, I said that human is the same as elixir.human, which is exactly the same as : elixir.human. So it is an atom. It has to be an atom, and the reason is because Erlang, all module names must be atoms. It's been prettified for us, so we can just say human, but it's really : elixir.human. So all three of these are going to return true for this particular example. It is a map. It does have a key of struct, _struct, and the value associated with the _struct is an atom. So for human, it will say that it is, or Mary, it will say it is a valid struct. So you see it's true. So that's how the is struct macro inside of, I think it was kernel, Elixir kernel works. Switched shirts. It's getting a little chilly out here, and it's fall day, and it's getting later. So we can actually evaluate this much as the macro itself would do by transforming the human struct into AST, and then we can generate AST from that by passing in the AST, unquoting it to make it Elixir, and then testing, is it a map? That's going to return true, and then we'll look to see whether the AST has a key of struct, which it does, so that'll be true, and then we'll look to see if the value of the struct is equal to an atom, and we know that it's human, which is an atom. So this all will be basically true and true and true, and when you then evaluate that will give you true, which it does. There's one other version of isStruct. We covered the case where you pass in a value and it tells you if it's a struct or not. There's another version of the isStruct macro which takes two arguments, one being the thing, the data structure you want to evaluate, the second being a particular struct name. So in this case you can say I want to see, is this a human struct? Which is true, obviously, but if you say is Mary an Ecto change set struct, it will say false. It's not. Kernel.tap is another relatively recent addition to Elixir, which is a nice thing to know if you're not familiar with it. It can be useful for debugging. It's also an interesting thing to look at how it's created in Elixir source code. So the way it works is here we're taking a map. You can take any data structure you want. Just as an example, I'm going to do two operations on the value inside this map. I'm going to update the value of A to be whatever the value is plus 2. So that's going to return a map with A:3. And then at the end, we're going to multiply by 2. So A is going to end up being 6. But let's say you had some complicated set of steps and something wasn't going right, and you want to know where something was going wrong. You can stick in a tap call here, and what it's going to do is it's going to pass along the value that's returned from step 2 here. It's going to pass it into step 4, just as if the tap function weren't there, but it's going to run this side effect for you. So you're going to say whatever the &1 is the current value of whatever gets passed in, and it's going to run as a side effect, it's going to run IOInspect on the value of A. So you can see that at this intermediate step, when it gets to step 3, line 3, the value of A is 3, because it's just inspecting it and printing it out for you. So it doesn't modify any of the other code. Everything else runs exactly as it would if the tap call were not there, but it runs as a side effect, so that you can then inspect the value or do whatever you want to it You could record it in a database inside the tap, let's say, if you want to record whatever the value was at this step. So how is this written? It's written taking a value in a function. It then so it's going to bind it's going to use bind quoted to take the AST and transform it so that you can just use it as ordinary Elixir code. Same with the value, and then it's going to actually execute the function. This is where the side effect happens. As we said, it's just going to return the same value. Whatever gets passed in is going to get passed through again. So when you call tap, the first argument is whatever the return of the previous line was. So the map is going to get passed in as value in the example above, and it's going to get returned. So that's what this last line is. Elixir always returns whatever the last piece of the last executed thing is. So the map will just get returned, but it's going to call the function with the map and just ignore the result of that. So this is the side effect. So that's why you would include tap, is for the side effect. So this is going to execute the side effect, and this is going to return the value again unchanged. Unquote fragments are a little confusing, but they're very powerful. And I had a little trouble wrapping my head around it. One thing that helped me understand how they work is this conversation here with Jose. So these four macros: def, which is a macro; def.p, which is a private definition, is also a macro. Def macro is also a macro, which blows my mind. I don't understand it, but it's what it is in a private def macro. All four of these things work a little specially in that they wrap the body of their do blocks inside an internal quote block. So they don't say quote, but they quote anything that gets passed into them. Where am I going with this? So if you look in the documentation, you're going to see an example like this, which is saying, so it's taking, this is going to create functions dynamically. And this unquote is different from, so this def call, as we just saw above, it's going to wrap the body of the do block inside an internal quote block. So this def, here's the do, it's going to wrap an implicit quote around this. So that's why you can call unquote here, is because there's already effectively a quote there. And this unquote here is allowing us to define the function based on the name. So we're going to create two functions here, one named foo and one named bar. So we're going to take the key and value pairs, and each of them is going to dynamically create a function with no arguments in this case. And the function name will be whatever the key of the pair is, and the value will be whatever the value is. So here's going to define a function foo, which is going to return, when you execute it, the value 1, and a function bar, which returns the value of 2. And this is how you would invoke the macro. Well, this is defined as a if you wanted to wrap this inside of a macro, this is how you do it. I won't go into the details, but I'm going to show an example here myself, which is based off of the documentation. You can see these functions do exist, and you can call them. Foo is going to return 1, bar is going to return 2, so if you add them together you get 3. A slightly different definition here. What I've done is I've expanded this so that you can pass in at runtime you can pass in an extra argument, or an argument, because it didn't accept an argument to begin with, and if you don't pass one in, it's going to default to a value of 0. And what it's going to then do is instead of just returning the value that gets defined at compile time, which is 1 and 2, depending on which function you're in, if the runtime argument extra will get added to that. So in this case, so again, if we just call foo and bar, we get the same value we got before, but I can now I can at runtime pass in an extra value, and then instead of just being a value of 3, foo earlier we saw is foo returns 1, but if I call foo2, that's going to be a value of 3. It's going to be 1 plus 2, and then bar normally returns 2, but if I say bar minus 4, it's going to be 2 plus minus 4, which is minus 2. So we have 3 plus minus 2, so we get a value of 1 here. So I just modified the example in the documentation by passing in a runtime argument, which defaults to 0, just as an example of how that works. But the main thing here to understand is that this unquote K allows you to dynamically create functions at compile time, which then exist at runtime that you can call at runtime. So sort of stepping back and looking at the big picture again. So what is metaprogramming and why should I care? Why should I spend time learning it? You may not need to. If you're early in your Elixir experience, you may want to stay away from it, but it's good to know that it exists and why it exists. If you want to understand the source code of Elixir, most of it's written in Elixir using macros. If you want to extend the syntax by creating your own syntax, you can create your own macros that allow you to do things sort of however you'd like to do it. You can define the while. If there's no while macro, you can define your own while macro. Similarly, you can dynamically create functions, as we just saw with what they call, it's a strange name, but it's the unquote fragments. You can dynamically create functions based on, here we're doing it based on key value pairs in a keyword list, but you could actually pull these values out of text files, and that's how Unicode characters are defined in Elixir, and functions built around Unicode like upcase or downcase. It takes giant text files and dynamically creates functions from those text files. We'll see some examples in, I think, tomorrow's the second episode of metaprogramming. Eventually I'll show some examples of dynamically creating functions in very useful ways from text files or other data sources. You can debug with greater confidence once you understand macros and how they work, because when you try to debug and you hit a macro, it can often be very confusing. That's one of the downsides of using macros, is that debugging can be hard for people, especially if they're not familiar with macros and how they work. You can create dynamic functions. As I said, we'll do that later. See that example. You can create your own DSLs. There are many that exist in the Elixir ecosystem, many of which you've probably used. I mentioned 3 of them earlier. There's also Surface, which is sort of if you've used React, Surface is trying to provide a React-like interface for doing live views. There's also many other DSLs. One that I've played around with a little bit is for RDF. It's a format for like graph databases, and somebody has done a very nice job of creating an Elixir syntax for interacting with RDF stuff. And Gremlix is similarly it's another. There's a Gremlin, which is a way to do graph database stuff, and Gremlix is an Elixir DSL for doing that. It's very helpful that somebody's done that, but all this is possible through metaprogramming. Create reusable compile time code by extracting code into use. You don't always want to reach for use, but when you want to use it, it can be very, very powerful. If you can get away with just using ordinary functions and modules, you're better off, but there are times when use makes more sense. And we'll go into examples of that. Also, optimizing your code. I mentioned earlier that logger, when it at compile time, it may just throw away your code. If it knows it's never going to actually log it because of the log level you're it won't even write it into your compiled code. compile time, code generation from external file. Oh, this is what I was just talking about. Yes. So if you look in the Elixir source code, which I'm here now, which, by the way, 21,000 stars. Congratulations, Jose. What an amazing thing you have built for everyone. There's a file called Unicode data.txt, which is a very large, almost 2 megabyte file containing all the Unicode data. And it gets updated periodically when they add or modify Unicode points, etc. I don't know all the details, but whenever that happens, Elixir can immediately leverage the new updated files, because it has a dynamic way to generate all the functions from the raw text files. Boy, I'm getting a little cold out here. Sorry, I'm having trouble talking because it's actually getting chilly out here. Unicode generates String.Unicode. So there's a module called String.Unicode which gets dynamically generated, and you can see from these notes here that it's using a variety of text files, and then it's basically compiling all those text files into a module called String.Unicode, which is what we use when we interact with strings in Elixir. So when any of these text files changes, we get to benefit from it right away, because they don't have to go in and manually change anything. They can just recompile the Unicode module within Elixir. And you can, if you look at the source code, I won't go into this in detail, but you can see sort of it's looking at the text files and reading them in and doing things with them, and building functions from them. Another nice thing is there's something called external resource. So you can tag a text file or other external file such that you will, if you're working with code in dev mode, it will automatically recompile your code if it notices that that file changed. So if, for example, you were working with, you were in dev mode and you updated your Unicode data.txt file, and it were tagged with this external resource, it would automatically get recompiled for you, which is very, very convenient. Oh yeah, so here's another example. So we just went over an example where you're dynamically generating functions from a text file. You could similarly, in Chris McCord's book, Metaprogramming Elixir, he shows in just 20 lines, he has a 20-line module that dynamically creates a bunch of Elixir functions for displaying all GitHub repos owned by a user, and functions, 2 functions per repo. One for displaying all details of the repo, basically all the metadata associated with the repo, and the other for actually opening up the repo, the GitHub repo in your browser. And he does the whole thing in 20 lines. So you just pass in a GitHub username, and it generates all these functions for you. It's amazing. Again, I encourage you to read that book. Get the book, read it. I'm not going to show the example here. I want to sell some books for Chris, but it's mind-blowing that he makes the API call and dynamically generates the functions in literally 20 lines. Another thing I mentioned, the dynamic compilation time code elimination. So it can look at this is actual source code for this. It defines a module attribute called levels. This defines all the levels, and then for each level it's dynamically generating stuff. So what's it dynamically generating? The function calls. So logger.level. So if you say logger.info, logger. Error, it dynamically generates these functions, and this is where it's actually happening. It's using the unquote fragment here to dynamically create the info, logger.info or logger.warn function. It's getting dynamically generated here, and one of the amazing, so then you can look at the maybe.log, it's calling out to that, and the reason it's maybe.log is because it may throw it away and just not even generate anything there. So you have macro.log and no log, and if you look at those, no log is just a no op. They have to do some magic here to tell the compiler, to basically trick the compiler into thinking that these things are getting used, because otherwise the compiler is going to throw in a warning, and they just don't want the warning there. But basically, it's throwing out the logger.info call if the log level is worn, for example. One last point before we finish this episode, I'll go to in the next episode I'll go through highlights of a number of macro metaprogramming talks that others have given, and go into some deeper, more extensive examples. But one last point before we finish this episode is that why do I need to call require before calling macro functions, or before invoking macros? And the reason is public functions and modules are globally available, but macros are not. So you need to opt in. And basically, when your code gets called, you need to tell the compiler, I need access to these macros, because this is happening at compile time. So it may or may not have compiled the macros that you want to use. And if it hasn't, and you try to use them, it won't know what you're talking about. And that's why you want to say require. And so if your code requires another module, the compiler then knows, oh, I have to go compile that other module first. And it will then compile that other module and then come back to your module and say, okay, now I can compile your module, because the things that it requires are now available to you. Functions are globally available, or public functions are globally available, but macros are not. And you need to, at compile time, say the require call needs to be there to ensure that the modules that you're calling macros in has been compiled before it tries to compile your code. So that's enough for this episode. I will do a second follow-up episode with the second half of the material I prepared for this. But thank you for coming back to ElixirZone, and I hope to see you in the next episode.